Now that we have discussed about the angle sum property, let's try to apply angle sum property in real life. So let's see how we can solve the problems in finding angles of a quadrilateral using the angle sum property. Applications in solving. So let's see one of the application of angle sum property in solving the math problems. For example, I have a quadrilateral where this is ABCD, a quadrilateral ABCD, in which this angle is 70 degrees, this is 80 degrees, (65°). This is x. So I know three of the angles, but I want to find the fourth angle. Then my angle sum property is more significant in case of such situations. For example, for this given problem where I need to find x, let's see how we can find x using angle sum property. Clearly we know that the given conditions are that angle A is given to be 70 degrees and my angle B is given to be 80 degrees. My angle C is given to be 65 and my angle D is given to be x, and we need to find the angle D, that is the value of x. So let's see how we can find the angle D using angle sum property. Now clearly from angle sum property, for quadrilateral ABCD, we have angle A plus angle B plus angle C plus angle D, all sum equals 360 degrees. So angle sum property for a quadrilateral where my sum equals 360 is what we have seen in the previous session. Now that we know each of the angles, let's substitute in the given angle sum property. So here for angle A, I substitute the value of 70 as given in the problem. So here I get 70 and then my angle B, which is 80 degrees, and my angle C, which is 65 degrees, and my angle D, which is x degrees, which I need to find, is all equal to 360 degrees. Therefore, sum of all this equals 360. Now my target is to find the value of this x. So let's see how we can find x from this equation. Let me add all this 3. 70 plus 80 is 150. 150 plus 65 is 215 degrees is what we get. Plus x degrees equals 360 degrees is what we get when it is further simplified. Now because I want to find x, I put x on the left side and this is taken to the right, so that this reduces to x degrees equals 360 minus 215 degrees. Next, now 360 minus 215 is 145 is what we see. Therefore, my x is this, is what I get in terms of angle sum property. So my angle sum property, when simplified through each of the angles substituted, I get my x, that is my fourth angle, which is 145 degrees. So given the three angles in a quadrilateral ABCD, I can find the fourth or the unknown angle using angle sum property. So my learning outcome here is that the angles of a quadrilateral can be found using angle sum property. In this case, my unknown angle, angle D, is found to be 145 degrees using angle sum property. Angle sum property helps us in finding the unknown angles of the quadrilateral 145 degrees in this example problem. Now that we have discussed about the different types of quadrilaterals like a rectangle, a square and a parallelogram, let's see the different other types of quadrilaterals also existing in the branch of mathematics. Today's session is about trapezium. Let's see a special case of a quadrilateral called trapezium. Let's see what a trapezium is. Imagine I take a four-sided closed figure formed by four straight lines such that I take one pair of straight lines to be parallel to each other. So what I do is I take line 1, which is arranged flat, horizontally flat. I take line 2, which I arrange exactly parallel to line 1. So first I arrange line 1, then I arrange line 2, which is exactly parallel to the line 1. So once I arrange in parallelity, I arrange line 3, joining the ends of first and second line. The other ends of the first and second line are joined by arranging the fourth line. So here I get a kind of a figure where one pair of lines are parallel, the other pair of lines are not parallel. So let's see what this special case of a quadrilateral is defined in mathematical sense. So when I join this, I clearly get a figure with a special case that one pair is parallel. So here I get a quadrilateral in which one pair is parallel. So ABCD is a quadrilateral with observations that AB is parallel to DC, but the lengths are not equal, only one pair is parallel. So in this case, the line segment AB is parallel to line segment DC. Such a quadrilateral in which one pair is parallel is called a trapezium. A trapezium is a quadrilateral in which one pair of sides is parallel. Let's take the definition in words. Quadrilateral whose one pair of sides is parallel is called a trapezium. A quadrilateral whose one pair of sides is parallel is called a trapezium. This being an example case of a trapezium where this line is parallel to this, but this is not parallel to this, is how we understand trapezium as a special case of a quadrilateral. Let's see the next special case of a quadrilateral in its own shape and its definition. This session is about discussion of kite. What is a kite? Now that we have discussed about a square, a rectangle, a parallelogram, a trapezium, now comes the discussion of a next special case of a quadrilateral in its own shape called a kite. Let's see the definition in brief. Imagine I take two equal straight lines and then join them out here like this. This is line 1 and this is line 2. I take two more equal straight lines and just join them from line 1 out here and then line 2 out here. So here is line 3 and here is line 4, such that this and these are equal and this are equal. Such a closed figure formed by joining four straight lines such that two equal straight lines are joined this way and the other two straight lines which are equal in length are joined this way is called a kite. The kite which I see, the flying kite. Is how I understand the shape of a kite. So here I have a kite flying and here I have a kite in quadrilateral. So such a shape is called a kite. So when I see this mathematically, I just understand that ABCD is a kite if this equals this and this equals this. AB and BC are called adjacent sides and AD and DC are called adjacent sides of the kite. These two are opposite sides and these two are adjacent because they are side by side. So if the adjacent sides are equal in a quadrilateral, such a quadrilateral is called a kite. So here my observation are that AB equals BC. One pair of adjacent sides are AB and BC which are equal, and the other pair of adjacent sides AD and DC are also equal. Such a quadrilateral form is called a kite. So let's see the definition of a kite. A quadrilateral whose adjacent sides are equal is called a kite. A quadrilateral with adjacent sides equal is called a kite. a special case of a quadrilateral whose adjacent sides are found to be equal. Kite as a quadrilateral, kite as a flying kite. Now that we have discussed the different types of quadrilaterals, starting with parallelogram, trapezium, rectangle, square, kite, we have many other properties which we connect. Now comes the relation between the different types of quadrilaterals which we're going to see in this session. Initially, I would like to find a relation between a square and a rectangle. How would we understand the relation between a square and a rectangle? So today's session is about square versus rectangle. So this is about finding the possible relation between a square and a rectangle. Let's see the discussion in brief. In order that I want to find the relation between a square and a rectangle, let me take a rectangle and a square separately. Imagine I take a square and I take a rectangle. Let's see the common properties identified between a rectangle and a square. Here, in a rectangle, I see that each angle is 90 degrees, this being a square and this being a rectangle. Also in square, I identify that each angle is 90 degrees. So in both the cases, each angle of a square and a rectangle is 90 degrees. Coming to the second property, I see that in a square, all sides are equal, but in a rectangle, opposite sides are equal. So I can understand rectangle through a square because for a square, when all sides are equal, all sides are equal implies opposite sides are equal to each other. Therefore, all sides are equal implies opposite sides are equal to each other. Therefore, this retains the property of a rectangle. Therefore, a square with each angle being 90 and opposite sides being equal to each other can be called a rectangle. Therefore, every square is a rectangle, but every rectangle cannot be a square because all sides are not equal. We only have the opposite sides equal, but all sides are not equal, which is an essentiality for a square. Therefore, we can say that every square retains the properties of a rectangle, but every rectangle does not retain the properties of square. Therefore, every square is a rectangle, but every rectangle is not a square. Is how we understand the learning outcome. Therefore, my learning outcome is that every square is a rectangle, but every rectangle is not a square. every square is a rectangle, but every rectangle is not a square, is the learning outcome, which makes me connect between understanding of a square and understanding of a rectangle as the special cases of a quadrilateral. Connecting square and rectangle. Is how I connect a square and a rectangle. Now next, let's see the relation between a rectangle and a parallelogram. Now that we have discussed about the relation between a square and a rectangle, where the learning outcome was that every rectangle is not a square, but every square is a rectangle. Similarly, let's investigate to search for some property connecting the trapezium, the parallelogram, and the rectangle. Parallelogram versus rectangle. So let's see the properties connected between the parallelogram and the rectangle. So here I consider a parallelogram, and in this column I consider a rectangle. Now we know that a parallelogram is in the shape of a sleeping or a slanting rectangle. Is how we understand the parallelogram. Now similarly, a rectangle is an erected property. Now let's see the properties in common. In rectangle, we have opposite sides are parallel. In parallelogram also the opposite sides are parallel. So these are the common properties identified between a rectangle and a parallelogram. Opposite sides parallel for a rectangle and opposite sides parallel even for a parallelogram. The next property is that in rectangle each angle is 90 degrees. So each angle is 90 degrees in a rectangle, but in parallelogram each angle is not 90 degrees. Therefore, I can see that opposite sides are parallel is the only condition for a parallelogram, and since in a rectangle opposite sides are parallel, irrespective of the condition that each angle is 90, every rectangle is a parallelogram. But every parallelogram is not a rectangle because it fails with each angle which must be 90 degrees. In parallelogram, each angle is not 90 degrees, but in rectangle, each angle is 90 degrees. So every rectangle is a parallelogram, but every parallelogram is not a rectangle. So let's make the learning outcome. Is how I make the learning outcome. Every rectangle is a parallelogram, but every parallelogram is not a rectangle because each angle is not 90. Is how I understand the learning outcome connecting the parallelogram and a rectangle. Similarly, if I take a square, let me introduce a square. Every square is not a rectangle, but since opposite sides are parallel, irrespective of the condition that each angle is 90, again I can say every rectangle or even a square is a parallelogram. Every square is a parallelogram, but every parallelogram is not a square. This is how I connect between a square and a parallelogram. The properties are similar to rectangle and square when connected with parallelogram. So in this manner, I can connect various properties where I can say that every parallelogram is a trapezium, or every rectangle is a trapezium, or every square is a trapezium, but every trapezium is not a parallelogram, etc. So we can interlink between two quadrilateral shapes in understanding through their common properties and the uncommon properties. So this is how we come into conclusion with various geometrical concepts like a kite connected with a parallelogram, or a kite connected with a square, or a rhombus connected with a kite. Is how we come across the different properties related to each other. Now let's see the special quadrilateral called a rhombus. As that we have already seen the definition of a kite, let's see how a rhombus is originated as a special case of a quadrilateral from the kite. Rhombus derived from a kite. Now that we have discussed about kite, let's recap the definition of a kite. So we know that a kite is a quadrilateral in which adjacent sides are equal. That is, when I take a kite, I form a kite when its adjacent sides are equal. What if I form a similar shape with all lines equal? That is, in this case, when I take the lines 1, 2, 3 and 4, I took 2 equal lengths and 2 pairs of equal lengths. What if I take all the 4 pairs of equal lengths? That is, if I have the line 1 to which there's another line 2 which is joined, and there's another line 3 and there's another line 4. That is, in a kite, this line is removed and a line of equal length is placed here, and this line is removed and there's equal line of this length put out here. Then I get this shape transformed into a shape where all lines are of equal lengths. A kite in which all the lengths are equal is called a rhombus. So this figure when formed is called a rhombus. A kite whose all sides are equal is called a rhombus. So here my rhombus is in the shape of a diamond. A rhombus is in the shape of a diamond with all sides equal. So I see that in this case, my side AB equals my side BC equals my side CD equals side DA. So this is how I get my rhombus whose sides are equal. Let's communicate in words. A kite whose all sides are equal is called a rhombus. A kite whose all sides are equal is called a rhombus. A rhombus is a four-sided figure with all sides equal. It's the shape, looks like a diamond. A diamond in the card. A diamond in the playing cards is a rhombus. The diamond which you see in the playing cards is a rhombus. A kite whose all sides are equal is called a rhombus, is the learning outcome I make out here. Now comes the biggest question on how we connect a rhombus with a kite. Let's see the relation between a kite and a rhombus. Rhombus versus kite. Now that we have discussed about the definitions of rhombus and kite, let's see the detailed properties and then connect through the common and uncommon properties. Here, I take the case of a kite and I take the case of a rhombus. Now here I have a kite whose adjacent sides are equal, and here I have a rhombus whose all sides are equal. Therefore, this clearly satisfies that my adjacent sides out here, being this and this, are equal, and my adjacent sides out here, this and this, are equal. That is, when I take it in the form A, B, C, D, my adjacent sides AB and BC are equal, and AD and DC are equal. Therefore, I clearly understand that this satisfies the properties of a kite. But when I take the kite, its all sides are not equal. Only the pair of adjacent sides are equal. So this does not satisfy the needs of the rhombus, is how we understand the relation between a kite and a rhombus. Therefore, my learning outcome in this case is that every rhombus which has its adjacent sides equal satisfies the properties of a kite, and hence every rhombus is a kite. But otherwise, every kite is not a rhombus, because all sides of a kite are not equal, and hence it is not a rhombus. So my learning outcome comes out to be every rhombus is a kite, but every kite is not, or I can say a rhombus is a kite, but a kite is not a rhombus, is how I understand. The relation between rhombus and kite. A rhombus is a kite, but a kite is not a rhombus, is how the learning outcome relates a rhombus and a kite. Now that we have discussed about the different types of special cases of the quadrilateral, Let's take the case of parallelogram and define its various mathematical properties connecting the parallelogram, a special case of a quadrilateral called parallelogram. Today's session is about properties of a parallelogram. Properties of parallelogram. One of the most important property is the property which connects the diagonal of a parallelogram. So let's see and revisit a parallelogram and its diagonal. We know that this is the shape of a parallelogram. A, B, C and D, in which opposite sides are parallel, is how we understand a parallelogram ABCD. Now, the property which connects the parallelogram is with the diagonal. So imagine I connect the diagonal AC. Now here AC is the diagonal which connects the two alternate points. Now when we see clearly the parallelogram with AC being the diagonal, the significance of the diagonal is that this diagonal cuts the parallelogram into two triangles. So here I have diagonal AC cuts the parallelogram ABCD into triangles, the two parts being the shapes of triangles. The first part of the diagonal is triangle ADC, and the other part of the triangle of the other part of the parallelogram cut by the diagonal is ABC, triangle ABC. Therefore, I have two triangles as cut by the diagonal AC such that ABC is one triangle and ADC is the other triangle. The two triangles, triangle ADC and triangle ABC. So let's see the properties connecting these two triangles in a parallelogram. So here the property states that a diagonal cuts the parallelogram into two equal triangles, or if the diagonal cuts the parallelogram, then the two triangles formed are said to be congruent to each other. That is, the property is triangle ABC is congruent to triangle ADC. Is how we connect the property. When two triangles are formed by the diagonal, the two triangles are congruent always in a parallelogram. Let's take the other case. If suppose I have another diagonal which joins from D to B. Now again I have triangle also for diagonal BD. Out here I have two triangles ADB and BDC which are also congruent to each other. If I take the diagonal, the second diagonal, triangle ABD is also said to be congruent to triangle BDC. Is how we understand the property of a parallelogram. a diagonal cutting the parallelogram cuts the parallelogram into two triangles, and the property says that for a parallelogram where the diagonal cuts the parallelogram into two triangles, the two triangles must be congruent to each other. This congruent to this and this congruent to this. There are two diagonals in a quadrilateral, diagonal 1 and diagonal 2. This diagonal makes these two triangles congruent. This diagonal makes these two triangles congruent, and this diagonal makes these two triangles congruent. The diagonal connects with congruency of triangles. Now let's see the property of a parallelogram which connects with the sides. Let's see the other property of a parallelogram. Connecting with its sides. So let's see the property which connects with sides. Parallelogram ABCD. Here is the parallelogram A, B, C and D. So clearly in a parallelogram we know that opposite sides are parallel. Now when the opposite sides are parallel, clearly I see that there is equal distance between the two parallel lines. But this equal distance is again cut short by two more parallel lines, where again there is an equal distance between these two parallel lines. So parallelogram is a closed region bounded between the pair of parallel lines. Therefore, it comes to an interesting geometrical property which arises out here. The pair of parallel lines makes a bounded region where the lengths are equal. The pair of parallel lines always makes the lines to be equal. So this side must be equal to this, and this side must be equal to this. That is, when the opposite pairs are parallel in a quadrilateral, their opposite sides are equal or also equal in a quadrilateral. Therefore, with this property, I come to a conclusion that the opposite sides AB is equal to DC and my AD equal to BC. Therefore, my opposite sides are equal. So here, the reason being that since opposite sides are parallel, therefore the opposite sides must be equal. Therefore, the property in a parallelogram is that learning outcome in this property is that opposite sides of a parallelogram are equal, as how I understand opposite sides of a parallelogram are always equal. Property number 2, opposite sides of a parallelogram are always equal. Now let's see the converse of the property which we have discussed in the previous session. Like for example, I have taken a parallelogram in which opposite sides are parallel, then that quadrilateral has its opposite sides equal. Now let's take a quadrilateral in which the pair of opposite sides are equal. Then will that be a parallelogram? So here it is converse of parallelogram. So let's see the converse as the properties of a parallelogram. The converse says if a pair of opposite sides of a quadrilateral are equal, then the quadrilateral must be a parallelogram. Then that quadrilateral must be a parallelogram, is how I understand the converse. That is, if I take the pair of opposite sides, I take the two lines of equal lengths and I take two pairs of equal lines and I form a closed figure, then that closed figure must be the shape of a parallelogram, is how the property defines. So the four lines, these two being of equal length and these two being of equal length, clearly I get a closed figure in which the opposite pairs being equal makes it indirectly to be parallel, is how we understand as the converse of the previous session. If two equal lengths are paired together to form a four-sided closed region, then mathematically we conclude that those pairs will obviously be parallel. So the parallelity derived from equal lengths is how the learning outcome comes out. Therefore, in this case, opposite pairs equal, opposite pairs equal implies opposite pairs parallel. So equality implies parallelity and parallelity implies equality. So opposite pairs equal implies opposite pairs parallel, hence a parallelogram. Is how we understand a quadrilateral reducing to a parallelogram, either the pair of sides being equal or the pair of lines being parallel. Parallelity implies equality and equality implies parallelity. If a pair of opposite sides of a quadrilateral are equal, then that quadrilateral must be a parallelogram, the converse of the previous session. Now next, let's see the other properties involved with parallelogram. Now that we have connected between parallelity and equality of opposite sides in a quadrilateral reducing to a parallelogram, let's connect with angles. What are the properties related to angles in a parallelogram? Angle properties. In a parallelogram. So let's see how the angle properties are defined in a parallelogram. So let's take a parallelogram ABCD. So here I have a parallelogram A, B, C, D. So A, B, C, D is a parallelogram in which opposite sides are parallel and of course equal. Now this is angle A, this is angle B, this is angle C, this is angle D. Now here A and C are called opposite angles, B and D are called opposite angles. angle A, angle C, angle B and angle D are called pair of opposite angles, are referred as pair of opposite angles. So let's see in today's session about the property which connects with opposite angles in a parallelogram. For a parallelogram ABCD, the property says that opposite angles of a parallelogram are always equal. That is, this equals this and this equals this. So the property here says that opposite angles in a parallelogram are always equal. Opposite angles in a parallelogram are always equal. Is how we conclude the property. That is, in this case, angle A must be equal to angle C and angle B opposite to that is angle D must be equal if ABCD is a parallelogram. For a parallelogram ABCD, opposite angles must be equal is how we understand the property connecting the opposite angles. Opposite angles in a parallelogram are always equal.